Well, I'm sad to say it, but we've arrived at our last talk at the Aerospace Village for DEF CON 31. Our ultimate presenter is Jacob Oakley. Jacob is a cybersecurity professional and author with close to 2 decades of experience on offensive cyber operations and security for space systems. He advises on strategic mitigation of risks and threats to globally distributed multi-domain network architectures. Jacob's presentation is on the complexities emerging from the intersection of space and cyber domains to professionals in both areas. He covers an introduction to satellites and space operations, the attacks that space assets face, and the vectors used to facilitate malicious activity. For the last time this year, please welcome Jacob to the stage.
All right, so that was a really long intro, but just to give a little more context, I hope this talk can kind of flesh out what you've seen here with Hackasat and give you a sense of what APTs and the people that are targeting these systems, how they look at them, how these systems actually are, and the challenges that we're going to have trying to protect them. So space, obligatory meme. All right, so like the intro said, I did offensive cybersecurity for a really long time, and then more recently have gotten involved in the space industry. And I found out that I used to think this is kind of what a space system was, right? There's something floating in space, and then there's some dishes on the ground that point and talk to it. And what I learned terrifyingly is that it is a lot like normal things that hackers gain access to, and typically things that have really weak security. So I learned that space systems actually have things like software-defined radios and data handlers and flight control computers and payloads and sensors, and all of those things are also computers. In fact, they often talk IP to each other, and they look like things that people compromise on a daily basis, but they're not protected in the same way. And I learned that on the ground, you have those same kind of components and more of a traditional attack surface kind of layout. Also, in satellites, you have 2 different portions of the satellite, and I'll use these words a lot through the presentation. You have the bus, that's the part that's actually flying the satellite. It has propulsion, it generates power, it's responsible for maintaining position, navigation, timing, that sort of thing. And then you have your payload, which is the reason the satellite's in space. It might be a camera if it's taking imagery, it might be antennas if it's doing something like Sirius XM radio, and so on and so forth. So to break it down a little bit more and show you just how much like a normal network it can be, you have crypto, hopefully, and you have software-defined radios or regular radios that are modulating that encrypted signal. But at the end of the day, you really just have 2 computers talking TCP/IP to each other. And if you were to compromise the ground station, there's potential that you could send traffic without even having to do complex altering of the way that communication protocol works. That's not to say that's how all satellites are, but that's certainly the case for some of them, which was a little terrifying to me. One more thing to talk about, and so primarily this talk is going to focus on low Earth orbit satellites. That's where I have the most experience, but I tried to expand where I could to cover any kind of attack surface that you have in space. But it's important to note, from a security person's perspective, you don't want to think about the fact that that thing you're trying to secure or that thing you're trying to hack if you're the enemy is not there all the time, right? You might only talk to it for 15 minutes at a time, and then you might not see it again for 2.5 hours or days, depending on the way the orbit's traversing across the Earth. So what do ground stations do? That thing on the ground with the antenna, well, of course, it's responsible for antenna movement. It's responsible for closing the link with the satellite and establishing communications. And that's where you're going to have, your tasking for flight and the payload are going to channel through that ground station, even if they're distributed on the ground. And that's also responsible for disseminating the things that it gets from the satellite, right? The space vehicle has, the bus like we talked about. It's doing power generation, storage, moderation. It's got PNT, that's position, navigation, and timing, and that's accomplished with things like GPS, which you're probably familiar with, or star trackers, which are things that just keep a map of the star, and if they lose GPS, they can try to find a constellation they recognize and triangulate their location off that. And then you have a sun sensor, which is a star tracker for just the sun, right? It tries to find the sun and recalibrate its orientation. You've got flight. Now, flight is traditionally you would think of something like propulsion, but they also have like flywheels, reaction wheels, which are really just these things that generate inertia, and that's actually how they move. They can adjust their orbit, they can move it out of the way of things. All stuff I learned about as a cybersecurity person. And lastly, on the space vehicle, you've got the payload-specific tasking and data storage. So a computer's life in space is difficult, and there are a lot of environmental challenges, and these computers have to be hardened to deal with all these things. So you have radiation, right? Computers don't like radiation. You have accumulation from being above the Earth's atmosphere, but you also have like single events. Something like a solar flare is going to be a lot more impactful on a satellite that doesn't have the Earth's atmosphere to protect it. You have temperature extremes, right? You're going from complete sun and then to complete darkness. Again, something computers don't necessarily like. You have a vacuum, right? And so connections and stuff like that can suffer from that. And then you have other space objects. These satellites you have to worry about, you're flying it. Is there other stuff headed your way? Is it man-made? Can they move? Do you have to move? So on and so forth. So this is just to give you an idea that the risks these things face aren't just cybersecurity related, but they actually all compound cybersecurity, and we're going to get into that as well. So operationally, there's a whole lot that goes into space systems, right? And things you don't think about as a normal cybersecurity professional, but all those things we just said, they have to test the spacecraft to see if it can survive all of those extremes, right? You have to send it to a table and shake it to make sure that when it gets launched on the rocket, the whole satellite doesn't fall apart, right? You have to send it in a vacuum, make sure it still functions. You put it in an oven, right? So on and so forth. Then you have to survive. You have to get a launch, which is very difficult. Then you have to deploy from your launch vehicle, stabilize, stop tumbling from getting ejected, and then finally start talking to the ground, right? And then once you're doing that, you still have to maintain and generate power. You have to worry about emanations interrupting your ability to communicate to the ground, and you, in some cases, have to worry about deorbiting as a requirement for being put in different orbits. So last thing before we get into the attacking these things, I gave a talk similar to this at a flight software workshop for NASA where they have the people that create the software for these systems, and a lot of people were arguing with me saying, well, satellites have things like backups. They have gold images so they can revert to it if they can't talk to the ground after so long. They have these scripts they call watchdog scripts that, if power usage goes over a certain level or certain things happen, predetermined actions in the satellite that'll protect it, and but the important thing to consider is these are all redundancy things, right? Like space, over time, organizations like NASA and the newer people playing in space, they're really good at redundancy. They're really good at, I need a third fail-safe to make sure I can still have my 10, 20 million, billion-dollar asset talk to me. But none of those are security focused, right? And if you have code execution on a component of the satellite, you're likely able to turn off these things or maybe set the watchdog to 0, right? If it uses any power, shut it off to preserve it, and then your satellite stops functioning, right? So targeting these systems is kind of a two-step process, right, as it is in anything, but we're going to walk through the specificity to space. So what is that thing that I want to attack, and how is it chosen? And what's the desired effect I want to achieve on that asset in space? So as a hacker, as a malicious APT, you're going to pick targets for one of a couple different reasons or methods. You're either going to pick it because it's a target of opportunity, and you know you can hack it because you found it vulnerable, and you don't really have any other reason to go after it other than you found a vulnerable thing. You may be targeting it based on who owns that asset. You may be targeting it specifically, that one comm satellite that does this one thing, and that's just that one satellite I'm going after. Or you might be targeting it based on what the satellite does, right? You're targeting all navigation satellites, for instance. Importantly, regardless of the method that you're going to have for target selection on one of these space vehicles, it's actually the mission or missions that space vehicle performs is what's going to heavily impact the way an APT is going to go after them as a target. So you could basically break down all different missions a satellite or space vehicle, for that matter, could perform into 3 high-level categories. There's missions that are sensing, there's missions that are emitting, and there's missions that are transiting something, right? You can sense radio frequencies, you can have a camera that's sensing, infrared, so on and so forth. You can have emitters like GPS, you could have emitters like, satellite radio, lasers, and that sort of thing. And then transit is, the space shuttle carrying cargo or a communications satellite transiting comms, right, where it's just responsible for moving something from point A to point B. So now that we know what those targets look like, what are the motivations, what are the reasons somebody would want to hack a satellite, right? We just walked through the finals of a competition where they were doing that, but why would those things happen, right? Why would I want to target that? It's pretty much be broken down into these 5 categories. You either want to collect something off of it, you want to use that satellite to redirect malicious activity to something else, you want to subvert the mission of the satellite, you want to potentially ransom it. That would be that target of opportunity, right? Somebody happened to find a satellite vulnerable and they try to ransom it. These things are very expensive, and the optics of losing it would be pretty bad for whatever organization owned it. Or you simply want to disable it. So regardless of what you want to do to the satellite and why you chose it as a target, I broke down the vectors that are going to enable that malicious activity to get to a satellite into pre-operational and operational. So by pre-operational, we mean things like design, development, testing, transportation, storage, and launch, right? So uniquely to space systems, you might finish designing a new program. So you have a $5 million satellite, you finish designing it and developing it, You then have to go put it in a warehouse at a launch facility and wait for it to get its ride into space. And that all presents unique challenges to these things. So then you have the operational vector, which is once it's developed and launched into space and it's operating, what are the things that you can attack while it's doing its mission and still in space? So obviously you can go from the ground to the space vehicle and from the space vehicle to the ground. And then you have inter-vehicle where we talked about earlier that whole bus payload thing. If I get malicious code execution on one of those computers on the satellite, I'm probably going to want to pivot to other things. And it's important to think about the fact that a lot of satellites up there, for instance, Starlink, right, they're hosted payloads. So you have one company who owns it and flies it, and you have another company or organization who has the payloads on that system, and one of them could get compromised and spread to the other, right? And then you have space vehicle to space vehicle. If you think about the constellations and mesh networks they have in space, if you're able to compromise one, you could potentially traverse across optical links and other things to other satellites in that same network, and then space to ground. So exploitation on these space systems, right, is often going to be tied to the mission, and it's also going to be impacted by the motivation for why you're going up there, to go and hack the satellite. If you wanted to ransom it, well, you're probably not going to attack the payload. You want to ransom the whole satellite, right? If you wanted to take it out of orbit, you probably want to go after the bus and not a payload. And then the other can be true of something like if you're trying to collect intelligence or you're trying to subvert a mission specifically, maybe it's easier for you to go after just the payload so that you have less likelihood of being caught. But certainly, many of those things can be accomplished by going after both. And anything that impacts the space vehicle is going to impact the mission. So what are those subsystems that we would want to exploit on a satellite to deliver the effect, the whole reason we have motivated to go hack it? There's the bus and payload subsystems, right? So I can go after tasking. I can impact your ability to receive tasking from the ground. I can mess with that. I can impact your ability to know where you are in space, what way you're facing, and what time it is. And if you can mess with that, then the satellite might not be able to point to the ground, close the link. You might not be able to do encryption handshakes, so on and so forth. And go after communications that way by messing with crypto keys, right? If I get code execution on your satellite and I change the crypto key, well, you can't talk to it anymore. Well, and I can because I know where it's at in space and I can point a dish at it and maybe close the loop. There's a lot more to it than that, but that's certainly part of the attack surface. And like I mentioned earlier, all those redundancy protocols that people have programmed into these flight computers can also be attacked, because if I can get privilege escalation on a satellite's operating system and I can tell the watchdog, hey, anytime somebody uses 0.1% of the CPU, shut the whole satellite down as a protective measure, right? And it will just keep doing that over and over and over again. And then the bus has, the one thing that's bus specific, whereas all those other things that could be a payload or the bus, right? You can impact PNT. You want to make sure the satellite can't talk to the ground, but I could also mess with the GPS of a payload so that it doesn't know where it's taking pictures of, for instance, right? But bus specific, you would want to go after things like power generation, distribution, and storage. That's probably the one thing I would say attack surface wise is particular to the bus, and you're unlikely to have a payload doing that itself. So to kind of wrap all that together, the way that I go after these vehicles, I came up with something called the Trex framework. It's not anything like the Sparta or any of these other highly intuitive and interactive things. This is kind of just a way I gathered my thoughts, but I thought it was a really useful way to frame the way a malicious actor would look at these systems, how they would target them, and the way they would think through attempting to compromise that space system's mission and get a desired effect. So I'm not going to read everything out here, but it's essentially what the previous slides were about. So what does it look like when somebody hacks a single satellite? And I've walked a lot of engineers through this because they don't believe me that their air-gapped system could be compromised. And I tell them, okay, well, you have a personal computer, right? And they say, yes. Oh, okay, and you charge your cell phone on there maybe, listen to music on it. And then you take your cell phone to work and you charge it on the server that hosts the ground station VM in your lab in your college or university. They say, oh yeah, maybe. Okay, well, I walk them through the malware and different tools that are developed to, for instance, hop across a cell phone, compromise your laptop, break into VMs that are hosted on there. And I tell them, well, if I can get into your ground station VM, I can probably get into your payload computer because there's an inherent trust between those two devices. And if I can get into the payload computer, maybe I can pivot into the thing doing the data handling for the whole bus. And if I can do that, then maybe I compromise your software-defined radio and you can't talk to the ground anymore. Or maybe you talk to me now and not your original organization as a satellite. Also, more importantly, as we get into the world of mesh communications and these big distributed systems, is the fact that let's say the people who have satellite radio, they don't actually own the satellite. They just have a payload on it that sends down the radio, right? But the satellite radio company gets hacked, and one of their satellites' payload gets compromised. And then with privilege escalation and moving across the computing devices on one satellite, I can actually, every time I talk to a new ground station via my payload, I can try to send malicious traffic down to the ground. Because again, why would my ground station think that it's getting malicious traffic from a satellite? There is a lot of inherent trust in these architectures and not a lot of validation of what's coming down. If I can do that, maybe I pivot into the flight computer. Even though it was the satellite radio company that got hacked and its payload and I sped into their ground stations, I can now pivot into the flight computer, and when it talks to the next ground station of the company that owns the satellite, I can compromise their ground station too. And like I said, with the whole mesh thing, if I compromise your optical link or just the communications you're using to talk to all the other satellites in your mesh, I can now proliferate across that as well. So most importantly, I think the thing I'm trying to get across here is I've learned more about space and cybersecurity, or what are these foundational problems that we're going to have to worry about and solve to prevent these sorts of things from happening. So there's a cost problem. There's always a cost problem in cybersecurity. It's seen as a tax. People don't want to pay for it. It's even more of a nuanced and difficult conversation in space because you're not only saying, hey, I need you to spend money to fix something, but you're saying, hey, I need you to use the next week's worth of contacts with your satellite to upload a patch or something like that, right? And so now it becomes even more difficult. I can tell you the space community is obsessed with flight heritage. And so if you can't answer this question, has that been done in space before? Has your tool been done in space before? And you say no, and you say, well, I'm not going to be your guinea pig to get into space. I'll just eat the risk and hope that I don't get compromised. And so that's one really difficult problem that'll have to be overcome. There's also a cyber warfare problem. So normally cyber warfare is not a great tactical choice for impacting something, right? If you told me that you cybered the anti-aircraft missiles and I have to fly my plane over them and I see perfectly intact missiles pointing up at the plane and I'm just really hoping nobody goes over there and reboots it so I don't get shot out of the sky, that's not a really strong tactical methodology for going after something. But in space, it's actually the only place where I want to kill something and have it just go silent and keep floating there. There's been examples in recent history where countries have shot satellites with missiles to prove they can do it, and they've actually polluted orbital fields with shrapnel going, over 10,000 miles an hour, and now people can't put satellites where those things were shot up. So not only are there a lot of challenges to securing satellites, but they're actually the most suitable target to cyber warfare. There's a big test and evaluation problem. So all of their tests that we talked about that are operational constraints for space systems, right? There's a vacuum in space, so I put the space vehicle in a vacuum. Space is hot and cold, so I put it in an oven, right? The rocket's going to shake it, so I shake it on a table to make sure it doesn't fall apart. There isn't a exercising of the security apparatus for these assets, right? There's things like the risk management framework, there's validation of compliance checks, but that's about as far as it goes. And it's kind of confusing to see an industry so obsessed with, you have to prove to me that this can survive in space, not have cybersecurity treated the same way. It's kind of like if you had a torque bolt that's going to hold something so tight, and you just said, well, I measured how hard I twisted it, so it should survive being launched on a Falcon 9 rocket, instead of going and putting it on a table that's going to shake it that hard for as long as it's going to take it to get into space, right? There's also an adaptation problem. All those things we just talked about, like temperature extremes and vacuums, those are solved problems in the space industry, right? I know how to shield something from radiation. If I know how long it's going to be up there, I can protect it, so on and so forth. Whereas, as we come up with cybersecurity solutions that are going to protect satellites, the enemy is obviously going to try to counter them. And so, the thing that we're only doing compliance checks on is also the only problem to the space industry that's constantly going to adapt to defeat them. There's a really big defense in depth problem. I hinted at a couple times that architecturally speaking, space systems, when you talk about the ground segment, space vehicles, other space vehicles, the components within them, they inherently trust everything they talk to. If you get to a ground station of a space system, you can probably do whatever you want because their satellites have no reason to not trust the ground. And the people that operate and own those systems are very nervous about putting anything in there that's going to potentially, quarantine something on the satellite and make it so they can't talk to it anymore. They're going to view that as a risk not worth taking. So modernization is also a problem for space. I think 15, 20 years ago, if you had people trying to hack satellites in something like Hack-A-Sat, they'd find it very difficult. The skill set needed to have the aerospace engineering, electrical engineering, RF engineering to actually maybe compromise these things that didn't have a lot of software definition would make it a hard target. Whereas now, you have things having more real-time operating systems that are open operating systems. They have, Linux, basically just strip down Linux on them, and they look more like a traditional target. And that's been done to make development easier, but that also means that this attack surface now looks like something that a lot more people could compromise. So another one is that there's a failure analysis problem. In space, there's a lot of rigor given to something goes wrong. If a satellite gets lost, they will convene a board of PhDs and all the different specialties, metallurgy, radio frequency people, electrical engineers, and they'll try to figure out for days and days and days, if not months, what went wrong so they can learn from it. But rarely in those conversations, if ever, does cybersecurity come up, and I've tried to communicate to people that cybersecurity could actually be, somebody could hack a satellite and do any kind of change to make it look like it was a vacuum problem or a radiation problem or any of these other things, right? But that's been given kind of last seat if it's even brought up at all. Most importantly, I think, is there's a huge disclosure problem. So almost everything in space is owned by a government or a military or a very large corporation that contracts with those types of people. And that means that, unlike on the ground, something like, we're never going to get a hammer like Stuxnet or the SolarWinds compromise to go beat people over the head with and say, we need to fix SCADA, we need to fix software supply chains, because we're never going to hear about these things when they get compromised for the most part, right? And that's why it's very hard to kind of build momentum and say, well, no, you do need to fix this because it could be really bad for you. And they're going to say, well, it hasn't happened to anybody yet, right? So lastly, for cyber and space tomorrow, we really need to catch up as a cybersecurity industry. I think space and cyber, and it's growing, but they need to do a lot of interchange. There's a lot of different technologies and a lot of attack surface and things that cybersecurity people are not used to securing. And so, by the time that's the highest risk that space systems view is cyber, we need to be prepared to address their problems. And that's it. I have a shameless plug up there, and I'm happy to answer questions.